Hello everyone. In this talk, we will be talking about online load balancing with Recourse. It's joint work with Sheely and Varun Suriyanarayana. So let's get started with the online load balancing problem. This problem, we have a collection of machines, M machines, and a sequence of jobs arrive online. There are N jobs that will arrive at the end of the instance. When a job J arrives, it tells us its load on various machines. For example, Pij denotes the load that job J would incur were it to be scheduled on machine I. And these could be different for different job machine pairs configurations. So the goal of the algorithm is to assign a job irrevocably to a machine I upon arrival. And then once you assign a job to a machine, the load on that machine increases by this value of Pij. So the goal of the algorithm is to find an assignment in an online manner which minimizes the maximum load of any machine. The load of a machine is simply the sum of the loads of all the jobs that are assigned to it. And of course, as with most online algorithms, the quality of a solution is measured through the competitive ratio, which is the ratio of the cost of the algorithm divided by the cost of the optimal hindsight solution. And we have to take a worst case over all possible instances. So lower the competitive ratio, the better the online algorithm is. So here is a simple toy example that also that explains the problem as well as indicates a lower bound instance for this problem. So imagine that at each time a job arrives, and the job has a very simple load vector characteristics. It has unit load on some two machines and infinite load on a bunch of other machines. So in this toy example, there are 8 machines, and the first blue job that arrives has unit load on the first 2 machines and cannot be scheduled on the remaining machines. Okay. So the algorithm, because everything is symmetric, all else being equal, the online algorithm may decide to schedule the job on the first machine. Now another blue job comes, can only go on 3 and 4, has infinite load on the other machines. So we decide to schedule it on this machine. And this can happen, right? We can get 4 jobs and we have decided to schedule it on all the odd machines. Now, unfortunately for the online algorithm, a new red job comes and it says it can only be scheduled on machines 1 and 3. Now again, due to symmetry, it doesn't matter which machine we assign this job to, so we send it to 1. Similarly, a job that comes only on 5 and 7, we send it to 5. Now you can see where this goes, right? There's going to be a new green job that says I can only go on to 1 and to 5, and the online algorithm has incurred a maximum load of 3 on some machine. Now, if this was all the instances, the optimal solution could actually do the entirely opposite, right? Every job, all the blue jobs could go to the even machines, which are all empty now, and the red jobs could then go to machines 3 and 7, and the green job can go to machine 1. So with that, the maximum load of that alternate assignment would actually be 1, which is what the optimal hindsight solution will do. So for this instance, any online algorithm deterministic online algorithm must incur a competitive ratio of at least 3. And we can extend this sort of lower bound to get a competitive ratio lower bound of log m when there are n machines. And indeed, that's one of the earlier results for this problem, that even for this simple type of restricted assignment setting where a job has a fixed load on some machines and infinite load on a fixed load which is machine independent like Pj on some machines and infinite on a bunch of other machines. Even there, we can get a comparative lower bound of omega log m on the comparative ratio. But what's surprising is that there's a very nice elegant algorithm due to Aspinus et al. Which shows that you can achieve this order log m bound. So there's a greedy style algorithm using a potential function which can get you this bound of order log n. So the main question that we are interested in this work is that all we can say about the online load balancing problem? The reason I ask this is that if you look at the offline problem for unrelated machines, we actually know extremely good algorithms. So we know a very elegant two approximation algorithm for this problem. So the question that we are asking is, can we slightly adapt the model, given that the existing model has tight results, can we slightly adapt the model to get similar guarantees even for the online problem? And that's the focus of this work. So we are going to look at online load balancing with Recourse. And what I mean by that is that the problem setup remains exactly the same as the first slide that I spoke about. except the following two changes. The first change is that when a job arrives, we have to assign it to a machine, but the assignments are not necessarily irrevocable. We can possibly change prior assignments of the earlier jobs. The objective is still to minimize the competitive ratio, which is the ratio of the algorithm's load upon the load of the optimal solution. But there's the twin objective of keeping the total number of reassignments or the total recourse as small as possible. Of course, if we are allowed arbitrarily large recourse, we could just resolve the problem after each new job arrival, and we'll maintain an optimal competitive ratio. Okay, so what's known for this problem? So there has been actually quite a bit of prior work for online load balancing with recourse, especially for identical machines. Um, but the most relevant result for our work is that of Gupta, Kumar and Stein from about a decade ago, which looked at the special case of restricted assignment, wherein a job has a size of pj on some subset of machines and infinite on every other machine. And for this setup, uh, the authors show an order log n competitive algorithm with a total recourse of order n, which means that after each new job arrival, we make constant number of changes on average and maintain a competitive ratio which is significantly better than a purely online algorithm can achieve, which is order log n. So what we show is that we can both improve upon this result as well as generalize the setting. So we can consider the unrelated machines, which is more general than the restricted assignment setting. So here now any job j can have an arbitrary load vector of pij on any machine I. And now we can show two types of results. One is we can show nearly best possible competitive ratio of 2 plus epsilon with a small increase in total recourse. So our total recourse is order n log n instead of order n. But notice that the competitive ratio has been driven down to almost what is best known even in the offline world. And we can also show that with order n recourse, we can get a slight improvement over the log n competitiveness. But both of these results hold true in the generalized unrelated machines model. So the first result is almost right in terms of the approximation quality, because even offline algorithms, the best known polynomial time factor that we know now is a factor of 2. Okay, so that's about the results. Let's get into the technical aspect of our algorithms. So before I get into our algorithm, let me start with a very simple toy example, which already illustrates the power of how a small amount of recourse can greatly help with the quality of solution. So let's go back to this sort of toy example lower bound that we looked at earlier, right? So this is a matching type of a problem where every new job has unit load on some subset of machines, n of j, and infinite load on every others. So we can look at it as a bipartite graph. The jobs are on the left side, the blue circles, the orange squares are on the right hand side, and we put an edge if the job has unit load on that machine, and we don't put an edge if you can't schedule a job on a machine. And suppose the instance is such that the optimal assignment has a max load of B star, meaning that we can find an assignment of the jobs to the machine so that every right vertex receives no more than B star many left vertices or jobs. And suppose the setting is in this manner, how we can come up with an online algorithm which finds an assignment close to a load of B star? That's the real question. And how much recourse will that incur? So here is a very simple, straightforward natural idea. You can call a machine free for a given assignment. Let's call a machine free if the current load is less than 3 B star, and the machine is saturated if the load is equal to 3 B star. And now we can construct the residual graph in the following manner. So let sigma denote the current assignment of the online algorithm. So sigma of j is the machine that job j is assigned to currently. And similarly, sigma inverse is the reverse assignment. So sigma inverse of a machine is all the jobs that are assigned to that machine I. So the way we can construct the residual graph is just a very natural method like we do for matching theory. We draw forward arcs from every job to all the available machines, all the machines it can be assigned to, which is the set n of j minus its currently assigned machine sigma of j. And we put backward arcs from every machine to all the jobs that are currently assigned to it. So that's the set sigma inverse of R. So given that we have constructed a residual graph in this manner, in this bipartite graph, so we'll have some forward arcs from jobs to machines and some backward arcs from machines to jobs. Here is a very natural online algorithm, right? So when a new job arrives, we can simply find the shortest path from the new job in this residual graph to a free machine. So once we find the shortest path from the new job to a free machine, that will be an alternating path because of this bipartite nature. That will be an alternating path from the job to machine to job to machine and so on. And alternate edges will be existing assignment, and alternate edges will be assignments that haven't been done yet. And we can simply swap the assignment according to the augmenting path. Okay? And that's the online algorithm. So how much recourse will this get? So clearly, if we can find a reasonable solution, all machines will have a load of less than 3 B star because we will never oversaturate a machine beyond a load of 3 B star. That's why we find the shortest path from a new job to a free machine, which has load less than 3 B star. So what's the total recourse? So the claim is that we can always find a free machine within a length of order log n. And the analysis is quite simple. Expansion of this residual graph that we've constructed. So let's say here is a new job, and imagine that it has n1 possible machines it can be assigned to. The set n of j has cardinality n1, and unfortunately all of them happen to be saturated. So we are not able to find a free machine yet. But the meaning of saturated implies that these jobs must be assigned to these machines, n1 machines, must be assigned to a lot of jobs, namely 3 n1 times b star many jobs in total across them. But now, where are these jobs getting assigned to in the optimal assignment? Right? We know that there is an optimal assignment of load at most b star. And by Hall's theorem, you can see that there have to be sufficiently many machines which are adjacent to these jobs. N1 of them can be in the top layer, so at least 2 N1 of them have to happen in the level below these jobs, if you draw this. So now again, if one of them is free, then we are in good shape. So let's assume that none of them are free. But you can see where this argument goes, right? So we've already seen that there's a geometric growth in the number of saturated machines as the depth of this exploration increases. So eventually we'll find a free machine within an order log n number of hops. And so we can change our assignment according to this manner. The new job goes to this orange machine. The first orange machine in this path undoes its assignment to that circle because that's a backward arc, and so on and so forth. So our total number of swaps we do for every new arrival is order log n. And we can always maintain a maximum load of 3 B star. So that's a 3 comparative algorithm with a total recourse of order n log n. So for this particular problem of this matching type of instance, the Gupta et al. Paper actually can get an improved analysis of order n recourse, total recourse, to maintain constant competitiveness. However, we have stuck with our analysis here using an order n log n recourse because it will help us down the line. Okay, excellent. So we have seen how recourse helps for this limited setting of this unit load restricted assignment. Now, how can we use these ideas for the general unrelated machines load balancing problem? So the idea is very natural. We formulate an LP relaxation for the load balancing problem. We first maintain an online solution for the LP relaxation with which can modify the fractional solution, both increase and decrease the fractional variables, but may ensure that the total change to the fractional variables is small. So that's the notion of low recourse. Once we do that, we have to round the LP solution online again with low recourse. And for all of this, we are assuming that we know this parameter T star, which is the value of the optimal solution, which is the make span or the load, maximum load of the optimal solution. Okay. So how are we going to, what's the natural LP relaxation? It's the standard relaxation that we have all seen oftentimes in scheduling theory. So there's a variable xij which denotes the extent to which job j is assigned to machine I. So the first constraint says that every job must be fractionally assigned to at least one machine. The second constraint denotes that the total load on any machine, which is sum over all j Pij times Xij, should be no more than T star, which is, we assume that we know knowledge of T star. And the last one says that these fractions are between 0 and 1. So what's one way? So now that we have seen that we can use shortest augmenting path kind of algorithms for solving low recourse load balancing problems, how do we generalize that to more the unrelated machine setting, especially the fractional variable? So a natural adaptation of these shortest augmenting path type approaches to these fractional allocation type problems is through the notion of flows. So what we do is we formulate a flow network and then use an augmenting path type algorithm to maintain fractional solution in the flow network. So what's the flow network? So we have these vertices for jobs, and it's an online flow network where a new job arrives that corresponds to a new vertex arrival in this problem. Then we have these blue square vertices corresponding to machines, and then we have a global sink. So the first simple edge we put is the edge from all the machines to the sink, which puts a capacity of 3 T star, and this 3 is like the slack we had for the free machines in the simple case toy example that we looked at. So we place edges from each machine to a global sink with a capacity of 3 T star. And what about the sources? Every job corresponds to a source, and the goal is to route one unit of flow from each new source or each new job to the sink. But what's the twist for this problem, right? Unlike a classical flow problem, where if Xij units of flow leave a node, then the same Xij units of flow enter the other endpoint of that edge. Here, because of the unrelated machine's nature of the problem, Xij units of flow leaving a job j becomes Pij times Xij units of flow entering this machine I. So we have to now solve a flow problem which has this scalar multiplicator on these edges. So that's actually, fortunately for us, it's a well-known class of network flow problems called generalized flow problems. So we introduce and study in this paper the online generalized flow problem, where these vertices arrive online and then each new vertex has to route unit flow to the sink. And we have to look at the total number of changes to the flow that we make. All right. So having constructed the flow network, what is our algorithm going to look like? The algorithm is a very natural algorithm in hindsight. So we can maintain the residual graph given the current flow of the terminals of the jobs that we have seen so far. And the residual graph has cost on these edges. The cost of a forward arc from job to machine is 1 per unit flow that we want to route. And the cost of backward arcs, interestingly, is 0, unlike negative cost, which we do for classical flow algorithms. And we do this because we want to track the recourse honestly. At least up to a factor of 2, having a cost of 0 on backward arcs precisely captures the total change that we do to the fractional solution. For example, whenever we increase the Xij variable, we incur a commensurate cost on the forward arc. And when we decrease the Xij variable, we don't incur any cost, but at least we don't gain back the cost that we paid at an earlier time step. Which is what would happen if we had put a negative cost on the backward arcs. And the algorithm is then very simple. Once we construct the residual graph, when a new job or a new source vertex arrives, we keep routing flow on the cheapest augmenting paths in the residual graph until we saturate 1 unit of flow. There is a star in augmenting paths because remember that this is a generalized flow network. So the notion of an augmenting path is not as simple as it would be for classical flows. In fact, augmenting paths can start at the new vertex and may not even end at the sink. It may end in what is called a flow absorbing cycle, and so on and so forth. But these are well studied objects nevertheless, and we can incrementally route flow on the cheapest generalized augmenting path, so to speak. And flow theory, this is a known result that if we actually put negative cost on the backward arcs, This algorithm is uh, is a generalization of the Ford-Fulkerson algorithm and is optimal for these min-cost generalized flow problems. However, the real question is we are putting a zero cost and backward arcs to track recourse in a more uh, honest manner. And our main result is to show that this algorithm is still not bad even if we put a zero cost. And we can show that we have a reasonable competitive ratio on the min cost flow. So with that approach, we can actually maintain an online solution to the fractional LP relaxation for this load balancing problem with a small number of changes to the fractional solution or low recourse. So the real question then, next question. So let's look at the rounding algorithm. So let x star ij be a good fractional online solution that we maintain to the LP relaxation. And suppose the maximum load of every machine is at most order of T star. What we are going to do is we are going to look at every machine and we are going to partition the jobs into various classes depending on the load of the job on that machine. So namely, B sub ik denotes all the jobs with the processing load Pij roughly like T star upon 2 raised to k. So once we get this partitioning of the jobs for this machine I, we are going to divide the machine into sub-machines with one sub-machine responsible for each class of jobs. And given this sub-machine and given a class of jobs, let f star ik denote the total fractional allocation of jobs from this class to this machine I. So it could be that there are 5 jobs in a particular class and in total they are allocated to an extent of say 1.2, then f star ik will denote 1.2. So given the fractional solution, we are going to now create this matching type of an instance where every job in the load balancing problem corresponds to a left vertex and every sub machine in the above characterization becomes a right vertex. And this right vertex is indicated by Vik denoting the submachine for I, k for the class Ik. And now the right vertex has a capacity and the capacities are not uniformly B star like we looked at in the earlier toy example. Each right vertex has a separate different capacity and the capacity is precisely this ceiling of f star Ik. So, and how do we place edges from left vertices to right vertices? It's a very natural way. A left vertex uj has an edge to a right vertex vik if and only if job j belongs to the bucket bik for machine I. So now we have a matching type of instance. The goal is to match all the left vertices to the right vertices while we respect the capacities. But here is the interesting part. We can now use the same algorithmic technique that we presented earlier, which is just shortest augmenting path to a free vertex using the free and saturated notions and so on. And we can maintain an online algorithm which has the following guarantees. Every job is assigned to a submachine. Every submachine gets at most order 1 times this f star ik jobs assigned to it, which means that totally this is a very good assignment, right? If the fractionally the submachine was receiving f star ik jobs, and in the integral assignment also it receives order 1 times f star ik, then the total integral make span is also no more than order 1 times the LP make span, which was order T star to begin with. The only catch compared to the earlier proof is that the right hand capacities now can increase or decrease based on the LP solution changing. But our simple greedy algorithm, which routes from every free machine to from every job to a free machine, is actually robust to all these variations, and similar guarantees hold true. This is why we had to use a simpler algorithm with weaker guarantees than the better algorithm of Gupta et al. So we can put the two pieces together to actually get an end-to-end algorithm which has order 1 competitive ratio and order n log n total recourse. So the fractional part maintains order n recourse and the rounding part loses an additional factor of log n in the recourse due to the shortest augmenting path that we have. With a different, more involved algorithm, we can actually maintain a 2 plus epsilon competitive online algorithm with a recourse of total recourse of order n log n. So that's why the first bullet point says you can get almost offline optimal guarantees with order log n amortized recourse. So every new arrival, we make order log n changes to the previous assignments, and the comparative ratio is almost what is best known in the offline world, 2 plus epsilon. So the main open question here is, can we improve this recourse while also retaining order 1 competitiveness? With that, I conclude. Thank you very much.